So now the housekeeping's out of the way, I'm delighted to introduce your speaker, Richard Farnell. Richard's one of our principal engineers at PDL. He's a chartered engineer through the Institute of Mechanical Engineers, and he's got over 11 years of experience in applying analytical tools and all kinds of things to complex stress problems. So everything from the gearbox of the Type 26 frigate to the Barrow submarine ship lift and a multitude of subsea high pressure valves, components, flow loops, etc. So in today's talk, Rich will endeavour to take the good work of the API committee through their development of API 17 TR8 and help you to gain an awareness of how it can be applied in practice. So Richard's going to be taking over for the next 30 minutes or so. After that, we'll have a few minutes to address some of the submitted questions and wrap up the session. So without further ado, over to Rich.
Okay, so thank you for the introduction, Michael, and good afternoon, good morning, everybody. So my name is Richard Farnell, and I'm Principal Engineer at PDL Solutions. I'm here today to present on a topic of increasing importance in the subsea industry, which is high pressure, high temperature, or HPHT. As this is quite an extensive topic, I'm going to focus primarily on how the move to more extreme operating environments affects the structural verification methodology. And this is particularly with respect to the design guideline API 17 TR8. So I'm just going to start by setting the scene, and to do this, I'm just going to try to answer a few fundamental questions in relation to API 17 TR8. So first of all, what is API 17 TR8? Which systems does it cover? Which systems doesn't it cover? What does it contain? And why is it being introduced? Okay, so what is API 17 TR8? Well, API 17 TR8 is a high pressure, high temperature design guideline, first introduced in 2015 and revised more recently in 2018. Although it's relatively new, it primarily serves to point us in the direction of more familiar ASME and API standards, depending on what is most appropriate for a given high pressure, high temperature system. It also provides supporting information which is relevant to HPHT systems, which isn't present in other standards. I think it's worth taking a moment to define what we mean by HPHT. So I'm sure some or most of you will have seen this graphic on screen in some form or another. Although these definitions are evolving all the time, it's widely considered that anything above 10 KSI and 300 degrees Fahrenheit is HPHT. At 15 KSI and 350 Fahrenheit, we transition to extreme HPHT, and at 17.5 KSI and 400 Fahrenheit, we move to ultra HPHT. Now, it's worth noting that if a system is below 15 KSI and 350 Fahrenheit, API 17 TR8 will simply direct you back to your existing API standards and methods of assessment. So by the definition you see on screen, at least, you could call this an extreme high pressure, high temperature design guideline. Okay, so what systems does it cover? Well, it covers any pressure containing components, including its seals and fasteners that come into contact with or are immediately adjacent to wellbore fluids operating at high pressure, high temperature conditions. So again, just to reiterate the definition from API 17 TR8, that's above 15 KSI and 350 degrees Fahrenheit. So in relation to subsea production equipment, which is clearly what we're talking about, we mean things like valves and chokes, Christmas tree flow lines, rigid jumpers, manifold piping, connectors, and intervention riser equipment. This is not an exhaustive list, these are just a few examples. It also states that the design methodologies referenced in 17 TR8 may also be applied to pressure controlling equipment. This is applied under the caveat that the design methodology can appropriately assess the applicable failure modes. So in essence, we're looking at mechanical failure modes rather than electrical or hydraulic. So what systems doesn't it cover? Well, it doesn't cover flexible pipes, either bonded or unbonded. It doesn't cover oil country tubular goods, such as drill pipe and casings, production risers, downstream pipelines, any structural member or ancillary equipment which is remote from the HPHT environment, and brittle materials. By brittle materials, we mean those which exhibit little or no plastic deformation prior to failure. You'll see the relevance of this exclusion when we move on to look at the design verification methodologies. Again, this is not an exhaustive list. These are just a few examples. So So what does it contain? Well, 17 TR8 is a relatively concise document. It's approximately 100 pages. However, it does contain a lot of useful information relating to HPHT design activities. The flowchart on screen forms the basis of the guideline. It serves to direct the user towards the most appropriate path to product qualification for a given HPHT environment. Now, I recognise that you won't be able to read the individual text boxes on this scale, or most of you won't be able to anyway. So I'll try to describe the paths in broad terms. So starting at the upper left position, we're asked, is our rated working pressure in excess of 15 KSI? If the answer is no, we're asked if our rated working temperature is in excess of 350 Fahrenheit. Again, if the answer is no, this is not deemed HPHT. If the answer to the latter question is yes, so we've got a system below 15 KSI, but in excess of 350 Fahrenheit, we're directed towards the provisions of API 6A, API 6X, and API 17D. Between 15 KSI and 20 KSI, we're directed towards the provisions of ASME Boiler and Pressure Vessel Code 8, Division 2, within which it has a design by analysis section, both a linear elastic approach and an elastic approach. Additionally, if the system is deemed to be fatigue sensitive, then we're required to assess its fatigue performance using a stress life SN based approach. Above 20 KSI, we're directed towards the provisions of ASME Boiler and Pressure Vessel Code 8, Division 3. Within this, it only has an elastic plastic verification route. Again, if we're deemed fatigue sensitive, now we have two options, two paths to go down, which is either SN design or a fracture mechanics based approach. The decision on which approach is required is based on the barrier philosophy, which we'll come on to. So essentially, the path selected determines the design margins, it determines the product specification levels, so the quality control requirements, and it determines the minimum hydrostatic test pressure. So broadly speaking, moving from left to right, the design pressures are increasing, the design margins are reducing, to counter this, the quality control requirements are increasing, and the structural verification complexity is increasing. Okay, so why is it being introduced? Well, there are a number of reasons, and I'll name just a couple here. So firstly, it reflects the direction in which the industry is moving. So depleting conventional reserves are leading to the development of subsea reservoirs at ever-increasing pressures and temperatures. So from 2000 to 2014, there were approximately 300 official HPHT wells drilled around the world. So the graphic on the right shows the number of the more notable ones, including Chardonnay, Satis, and Macondo, to name a few. And there's no reason to think that the development of HPHT wells is going to do anything but increase in the coming decades. Hence, it's good to have a design guideline which is specific to this. Secondly, as we saw from the previous slide, there are a number of routes to design verification currently available to engineers. A number of these routes are not subsea specific, and it's difficult for engineers to know how applicable certain aspects of the code are to their subsea applications. So 17 TR8 aims to give some clarity in relation to this. In particular, it does a good job of clarifying subsea specific load designations and appropriate load factors for normal, extreme and survival conditions. These are all absent from the ASME standards. Thirdly, there are a number of manufacturing and installation issues which become more problematic as the equipment becomes bigger and heavier. So for example, mechanical handling becomes more difficult, ensuring adequate and consistent through-wall material strength properties becomes more difficult. And it's intended that by utilising more advanced analytical tools and adhering to stricter product specification levels, some of the design margins can be tightened, leading to more efficient designs which alleviate some of these issues. Okay, so what's changed? Why do we need to change the assessment methodology as we increase in pressure? Well, geometrically speaking, the transition at 15 KSI to higher rated working pressures tends to change designs from thin wall to thick wall. So typically our flow requirements dictate the bore size of our structure. So to resist the increase in pressure, we can do little but thicken up the wall. Now on the subject of walls, and to break up the technical content, here's a nice image of the Roman Emperor Hadrian's wall, which is just a mile or so from our offices in the north of England. This wall was built nearly 2,000 years ago and is still standing. So I think we can all say the Romans certainly knew a thing or two about wall integrity. And for the guys outside the UK, just to give you some context, so here's a little graphic showing our offices here in Northumberland with Adrian's wall spanning the country. So back to the technical stuff. So when is a thin wall thick? When is a thick wall thin? Well, fortunately, ASME have provided us a definition which helps us to determine this. So the two expressions on screen, the first is given in terms of the inside radius and the wall thickness. The second given in terms of the outside diameter and the inside diameter. They're mathematically equivalent. And essentially, what we're saying is if the inside radius or the thickness is less than or equal to 4, then it's a thick wall. Equally, if the outside diameter or the inside diameter is greater than or equal to 1.25, then it's a thick wall. So to give some context to these ratios, I've drawn out a thin wall cross-section on the left, a thick wall cross-section on the right, and then a wall section at the transition point in the middle. Now, wall thickness in itself doesn't determine that it has to be assessed in any particular way. So to understand that, we need to look at some specific stress considerations for thick wall structures operating in high pressure environments, which may otherwise be unimportant for thin wall structures in low pressure environments. Okay, so firstly, internal bore yielding, also known as autofrettage, can occur. So with the high pressures, we get high radial and hoop stresses, which are developed at the internal diameter of the structure. And this can give rise to stresses in excess of the elastic yield limit and can result in regions of plasticity. So for the example of the image on the right, this is represented by a material coloured in red. So for ductile materials, this can be allowed to extend some way into the wall thickness without compromising the overall integrity of the structure. Moreover, autofrettage can be introduced by design, as the residual compression that's left on that inside surface can be beneficial in terms of retarding crack growth. So it's just something that is specific to thick walls that we never really had prior to this. We also need to be aware that these high internal stresses are concentrated further at sharp corners, such as bore intersections and seal pockets. These are likely crack initiation sites for cyclic failure modes such as fatigue. And thirdly, the transition from thin to thick wall also has a tendency to change the likely fatigue failure mode from leak before burst to fast fracture. So what do I mean by that? Well, as a crack propagates, assuming it starts at the inside surface, as it propagates through the wall thickness of the structure, it grows in both the radial and circumferential directions. So for thin wall structures, it tends to reach the outer surface, having propagated only a small amount circumferentially, meaning that much of the cross-section is still intact and can contain the pressure. The crack reaching the OD results in a leak path, which can be detected. Hence we call this leak before burst. And this gives us the opportunity to intervene prior to fracture. For thicker wall structures, the crack has much further to propagate radially, and as such propagates much further circumferentially too. So this can result in a crack reaching a critical size such that the remaining cross-section cannot contain the pressure and fast fracture occurs. So this obviously happens before any leak can be detected and any intervention can take place. A further consideration, which may be overlooked for thin wall vessels at lower temperatures, is that for thick wall structures, there is likely to be a non-uniform temperature profile through the component, resulting in differential thermal expansion and potentially significant thermal stresses. This may also exist due to differential thermal expansion rates if more than one material is present. Although this is not unique to high temperature applications, the increased change in temperature makes this effect more pronounced and necessary to consider.
We'll just let Rich have a quick swig of water at this point and give you a timely reminder that any questions can be asked through the questions box. We've had a couple so far, so many thanks for that. And we've also had a question just on the logistics of getting information across after the event. So I was going to mention this at the end, but just to clarify, we will be sending you a copy of the slides via PDF to your inbox, and there will also be a link to a recording of the webinar, again to your inbox, so you can listen to it at your leisure or share it with your colleagues. I think Rich is good to go, so I'll hand you back.
Okay, so how does this influence the structural verification method? Okay, so to understand this, we must first look at the common methods of assessment employed for low pressure systems. So the most common form of structural integrity check, particularly for complex geometries, is to use a numerical model to predict the elastic stress distribution in the component. So here we've got a valve body with an applied pressure, and the response in terms of the stress distribution has been predicted. Okay, so how do we say whether this is acceptable or not? Well, what we typically do is we find critical sections in the structure and we draw stress classification lines, and we determine what the stress is along each of these paths. So that stress is shown here in green on this line. We then take that stress and we apply stress linearization techniques to extract the membrane stress, shown here in blue, which is the average stress through the wall section, and the membrane plus bending stress, which is this red line here. So the membrane plus bending stress accounts for the membrane, obviously the membrane and the bending component, but excludes any effects from peak stress components and structural discontinuities, because these are less important for sectional strength. Once we've evaluated the values of the membrane and membrane plus bending stress, we then compare this to API and ASME limits. So for a ductile metal, this is typically in the range of the membrane stress being compared to 2/3 of the yield strength, and the membrane plus bending stress being compared to the yield strength. Okay, so why don't we just keep doing this? Well, the excerpt on screen is taken from ASME VIII Division 2. In essence, this states that the linear elastic stress analysis method may return non-conservative results for thick-walled vessels. Now, the reason for this is that the stress classification procedure does not accurately represent the nonlinear stress distribution observed in thick-walled structures. This is particularly true around structural discontinuities and is enhanced further if yielding occurs. Now, we've already discussed that surface yielding is commonplace and perhaps maybe introduced by design for thick-walled structures in high-pressure environments in terms of autofrettage. There is a caveat to this in that the linear elastic method may still be used for heavy-walled vessels, provided the von Mises equivalent stress does not exceed the elastic limit through 5% of the wall thickness. This applies for the worst case loading combination, which includes hydrostatic test. Okay, so what's the alternative? Well, an elastic plastic assessment, of course. Well, in this method, we're going to look to more accurately represent the component behavior beyond the elastic limit. So in oversimplified terms, the procedure is as follows. We build a numerical model. We can see here, we're getting a valve body. We derive and assign nonlinear material models. So the material models shown here are all common materials used in subsea applications. The strain hardening region in all of these materials is very significant. And bear in mind that the linear elastic approach only accounts for this small region of the material behavior. It takes no account of the behavior beyond that point. And then once we've defined that, we load the model to failure. So let's have a look at what this might look like on an example valve component, assuming this animation works. So we can see here, as the pressure increases in the valve, we can see plastic hinges starting to develop, and we can see that the displaced shape is becoming highly distorted as sections approach collapse. So at this point, the numerical model cannot achieve equilibrium and returns a non-converged solution. So I'll just let that play again, and you'll see the plastic hinges developing in and around the branch here. Okay, so let's have a look at this in slightly more detail. So as we just said, the plastic collapse is characterized in the analysis model as an inability to achieve equilibrium for a relatively small increase in load. So modeling the actual material response allows us to simulate something much closer to the true response of the structure. And this is especially true in the most critically loaded regions. So as local regions yield, the load redistributes into the surrounding elastic material, which is stiffer. As the load continues to increase, this redistribution continues to occur until the remaining elastic section is insufficient to carry the load. At this point, we'll get significant displacement for a small increase in load, and the model will not be able to achieve convergence. So by interrogating the results in the example on screen, so the image on the right here, we can see regions in excess of the yield strength are shown in red, and we can see huge regions like that. And regions in excess of the UTS are shown in grey, and we can see a significant enough proportion here such that we've observed a sectional failure. So if we take this, so basically at this point, whatever pressure is being applied, we take that as being the plastic collapse pressure. So applying code-specific design factors, we can reduce this plastic collapse pressure to a maximum working pressure, shown here in the middle, the stress distribution at that load level. And essentially, provided the maximum working pressure exceeds the design pressure, the component passes the assessment, as shown here. So in addition to accurately predicting the collapse load, the ability to represent the reduction in stiffness as the material yields also allows a better prediction of component deformation. So this can give us a better understanding of likely limits for functional failure modes, such as loss of sealing, which are dependent on the relative displacements of sealing surfaces. So having hopefully gone some way to explaining the need for the alternative verification routes at higher pressures, I'd like to return now to the API 17TR8 design flowchart. I'm going to discount the verification routes for the lower pressure systems and just focus on what we do for the most extreme cases. So as we've discussed, both ASME VIII Division 2 and ASME VIII Division 3 have a nonlinear elastic plastic verification route. So let's take a few moments to compare the two methods. So from a close-up look at the flowchart, we can see that many of the required checks are mandated by both methods. So we can see here we've got global plastic collapse, we've got local strain limit checks, we've got ratcheting check, hydrostatic condition, and then some form of fatigue check. So let's have a look at the primary differences between the two methods. So one of the major differences is in the design margins which are employed. So here we have a table which lists the normal load condition design margins for a number of fairly typical assessments. So we have plastic collapse excluding factor thermal loads, we've got plastic collapse including factor thermal loads, we've got a local strain criteria check, and we've got the hydrostatic test assessment. So looking at the first three assessments, it's clear that there's a fairly significant reduction of approximately 25% in the applied design margin between the two codes. So here we're going from 2.4 down to 1.8, 2.1 to 1.58, and 1.7 to 1.28. It's slightly more for the hydrostatic test case, so we've got a reduction of about 37.5%, but this is a little skewed as the two analysis methods use different material models. So Division 2 uses the full strain hardening model, which we saw on the previous slide. Division 3 uses an elastic perfectly plastic material model, which allows no strain hardening beyond the yield limit. But nevertheless, there's still a significant reduction. Okay, so the trade-off is the higher product specification level which is required. So essentially, there are additional quality control requirements which need to be adhered to allow the design margins to be reduced as significantly as they are. So a few examples are shown here. Again, this is not an exhaustive list and you should refer to the relevant documentation. But essentially going from product specification level 3/4 to product specification level 4 as required between Division 2 and Division 3. This may result in the need to achieve higher Sharpie toughness values. There may be additional limits on ovality and misalignment. There may be a great requirement for post-hydrostatic test inspection, non-destructive examination to detect any flaws within your structure of critical sizes or of a maximum size, and a requirement to develop the fracture toughness properties. So fracture toughness properties is a fairly big one. This is an input to the fracture mechanics assessment. Lots of the available information on fracture toughness isn't developed for subsea applications and doesn't account for the likely temperatures that we deal with, and also like sour service environments, things like that. So there may well be a requirement for you to develop these properties for your particular materials at your particular loading environments. So it's clear then that although the use of ASME Division 3 can have advantages in terms of reduced design margins, which may then translate to cost savings in design, material costs and handling, and will ultimately produce a more efficient design, it may also require more rigorous constraints on material testing, inspection and manufacturing quality. It's therefore important that operators and manufacturers who elect to follow this route clearly identify and value assess the benefits and constraints for the entire life cycle of the structure. So I mean, there will be significant cost involved in adhering to the higher product specification level 4 requirements, and this should be weighed up against the cost savings from the reduced design margins. Another key difference is so if you're following the division 3 verification route, there's a lower minimum HYDROTEST value, which is mandated. So we can see here where we can drop from 1.5 times rated working pressure to 1.25 times rated working pressure. So this can be very useful, practically speaking, particularly for very high rated working pressures. So for instance, if we have a 20 KSI system, testing at 25 KSI may be significantly easier and cheaper than testing at 30 KSI. In terms of guarding against fatigue failure, both methods require a fatigue screening process to be undertaken. So the fatigue screening should follow the approach described in section 5.5.2 of ASME VIII Division 2. It can either be based on experience of similar equipment operating in comparable conditions, or if you don't have the benefit of that, an assessment needs to be performed considering the material construction, the construction details, and a load histogram of the expected loading regime in order to make the judgment. If a fatigue assessment is required, the Division 2 route mandates the user to satisfy a stress life approach, an SN type assessment. A fracture mechanics based assessment is optional, however. If we're following the ASME VIII Division 3 route, the mandated method is dependent on the barrier philosophy. So essentially what this means is that if fatigue failure will result in a loss of containment, the fracture mechanics method is mandatory. If a secondary barrier will be employed to contain the flow, then the SN method may be acceptable for the primary barrier. However, some kind of assessment of the secondary barrier would then need to be made. For example, is the secondary barrier fatigue sensitive, or will intervention occur in the short term? If it's deemed that the secondary barrier is fatigue sensitive, then a fracture mechanics assessment would then need to be performed on this barrier. So let's have a quick recap on the essential differences between the ASME Division 2 and ASME Division 3 verification routes. So Division 3 has reduced design margins compared with Division 2. It also has reduced minimum hydrostatic test pressure requirements compared with Division 2. To counter this, we have higher product specification levels, so more tighter quality control requirements. A fracture mechanics assessment is potentially required if following the Division 3 route, which is based on the barrier philosophy, as just discussed. But fundamentally, Division 3 allows for the design of thinner walled components for a given design pressure. And the benefit of this is that we can help to reduce weight, cost, and manufacturing problems associated with heavy walled vessels. So to summarise what we've discussed in terms of API 17 TR8, the component wall thicknesses are increasing in response to the higher pressure demands. We now have additional stress considerations for thick wall structures under HPHT, which include internal bore yielding or auto frettage, fast fracture failure modes as opposed to leak before burst, and increased effects from thermal gradients due to the higher delta T's that we're going to be imparting on the system. So with increasing pressure and temperature, the recommended analysis methods are becoming more complex. So we're moving away from the linear elastic approach to an elastic plastic approach. We're moving away from SN fatigue and towards fracture mechanics based approaches. So through increased analytical complexity and higher product specification levels, the design margins and test pressures can be reduced, which is what we just looked at with ASME VIII Division 3 versus ASME VIII Division 2. And essentially API 17 TR8 provides a useful reference resource for aiding the design verification process of high pressure, high temperature equipment. More than that, it fills a lot of gaps for subsea specific applications where the ASME standards are just not very clear for our particular purposes. It's worth mentioning that 17 TR8 is not a standalone document, and it is to be used in conjunction with other design codes which you're likely to already be familiar with and have used in the past. So for instance, API 6A, API 6X, API 17D, and the two ASME boiler and pressure vessel codes discussed. So this concludes our short presentation on API 17 TR8. Thank you for your attention over the last half an hour or so. Next, we'll try to answer a few of the questions which have been submitted.
Thanks, Rich. That was really informative, and thanks for taking us through that. So yeah, we've had a number of questions submitted during the talk there. Actually, a few people have picked up on the same question, so we'll start with that one since it's popular. Actually, one of our BVAA Future Leaders program colleagues raised this one amongst a couple of others, and it was to do with the material curves. Are these actually coming from testing, or are they from calculation or code? Or
okay, so yeah, so the material curves, you can use actual material curves if you have it. So if you've gone and you've developed, if you've done some testing and you've developed true material behaviour for your particular material, then you're welcome to use that. In lieu of that, if you don't have that information, then synthetic curves are available to be developed. So if you're following ASME Division 2, I think there's a methodology stated in Annex 3D, and somewhere in KD 231 is the method for developing the same curves for ASME VIII Division 3. I think they're both comparable and they essentially produce the same curve though.
Okay, thank you very much. Got quite a specific question here. Can we go back to slide 24? Is that within our powers?
I think so.
Yeah. So this is about the pressure test, the 1.5 times recommended working pressure versus 2 times recommended working pressure.
Is it this slide?
Yeah, that's right. So the question was just whether or not the Div 2 pressure test should be 1.5 rather than being 2 times.
Sorry. Yeah. So this isn't the actual test pressure. This is the assessment pressure. Right. So in order to pass the assessment Division 2, we need to achieve 2 times rated working pressure. That's against the physical test requirement of 1.5 times rated working pressure. Within Division 3, we essentially just need to meet or achieve the exact pressure that we're going to do on test. However, the conservatism is included by using an elastic perfectly plastic material model which has no strain hardening. So sorry if there's some confusion there. It's the assessment pressure rather than the actual physical test pressure.
All right, that definitely clears that up. That's great. The other one that came in just before was when we're talking about fatigue, how do we actually know if the product is likely to be fatigue sensitive?
Okay, so there's, as I kind of briefly mentioned in the slide, section 5.5.2 of ASME VIII Division 2 essentially gives you a procedure for determining whether or not your component's likely to be fatigue sensitive. So the first part of that is saying, well, if you've got existing structure, an existing structure which is like for like, is comparable, and that's, you know, it's survived for a long period of time, then we can infer a level of confidence in terms of fatigue performance from that. If you're just moving into a new market, a higher pressure market, you're not going to have the luxury of that. And there are two methods, method A and method B, which basically allow you to figure out whether or not it's fatigue sensitive. They're both step-by-step processes. The first is only applicable to materials below 80 KSI, I think. The second method is applicable to all materials, but it's essentially a means of looking at your loading regime and counting the number of cycles in which you're going to exceed certain load levels and comparing that to certain limits within the code.
Okay, no, that's great. I'm going to pick one last question just before we draw things to a close today. So this one was, does 17 TR8 provide guidance or any assessment methods for fasteners?
Yes, so there's a whole section within 17 TR8. I don't know offhand, maybe section 7.2 or something. Yeah, so within that, it basically it gives you lots of information on how to assess fasteners. Fundamentally though, the assessment of fasteners is done using a linear elastic approach. I guess, you know, we don't really want to allow our fasteners to go plastic. If we do that, we're likely to lose sealing or something like that within the system. So we tend to be limited by the limits from, I think it's 17D, which I think that sets at 83% of the yield strength for fasteners. So basically we're working towards that. But what we also need to bear in mind is, you know, the fasteners can fail not just through tension, but also through shearing the threads. So we need to make sure we've got adequate thread engagement in order that our fasteners fail in tension rather than ripping out the threads. And I think it's also we need to pay particular attention to this when we've got blind holes in components where the material isn't as strong as the bolting material. So we need to make sure we factor that into the shear stress or the shear strength of that blind tapped hole.
Okay, excellent. I take it there's a bunch of people around the world now just checking whether it's 7.2 and whether you've got that right.
Yeah, I kind of hope it isn't right. It's a bit sad.
Good stuff. No, thanks for that. I'm afraid we've run out of time to take or to deal with any more of the questions, but please rest assured that anything that you've asked during the course of the webinar or anything that you want to pose afterwards, you can actually just send through to either Rich or myself, and we will answer the questions via email. So don't worry, we will get there. So just to confirm, as I mentioned, this was the next in the Knowledge Library series. We've got another one in the planning at the moment, which is on structural capacity of premium connectors. That should be with us in early autumn. So when I say early autumn, you never know, it might be September. So please keep a lookout across the usual channels through LinkedIn, etc. You will also get, if you've asked a question, you'll obviously get a response in your inbox, but you will also get, as I mentioned earlier, a recording link so you can go back and listen, and you'll get a copy of the slides as well. And feel free to disseminate that in your company amongst your colleagues, and if any of them have any questions, feel free to point them towards us. So that brings us to a close, really, and I've just got the final task of thanking Rich for sharing his knowledge today, so thank you, Rich. And to thank Kate and Linz for their work behind the scenes in setting the webinar up, and to thank you all for joining us. Thank you.